Now the final thing that we need to do is we need to solve the radial equation. We found this equation previously when we did the separation of variables in the first part of this series, and this is what we got. Now, last time I wrote it, I did use here k instead of L times L plus 1, but because in part 3 we already showed why this k has to be L times L plus 1, then I'm just going to use it here. Okay, so how can we solve this equation? Well, first, let's take a look at it. We have here this derivative on things that depend on r. So the first thing that you might try is say, well, what happens if we just take this derivative? So let's just do that mainly to see what happens and see if there's maybe something that looks better. So if we take this derivative, we get 2r dr dr, and because of the product rule, now we get plus r squared d squared r dr. And well, all of this is going to be the same. So this is what we get, and it doesn't really look like it's going anywhere. It isn't really much simpler. So maybe what we have to do here is determine some sort of change of variables. Now here, obviously change of variables does require to have some experience doing these things. But something that might give us a hint is just see, okay, here we have r times big R, and here we have r squared times this second, whoops, I'm missing a 2 here, by the way, times this second derivative. So something that we might want to try is just, okay, let's just call our new variable u, you can call it whatever you want, and just say this is small r times big R, and just see what happens. So the idea behind this is that if we now put this variable into our equations, we want to get something that is of a simpler form than this. So let's do that. I'm going to get rid of this because this was only to see if it would have helped. It didn't really help much. Now we have to determine, and how can we put it in here? Well, here there's only an r, so we need to know how r depends on u. That is something we can do by just from here finding r. So finding not r, but a big R. So big R is just going to be u divided by small r, right? Because our new function is u. So that way we get rid of this r and this r, but we still need to know how this dr over by dr, this derivative of big R with respect to small r, what that is in terms of u. And to do that, let's just take the derivative on both sides and find what it is. So dr by dr is going to be, and now this is obviously u of r, so here we have to apply, well, the product rule or the quotient rule. I like to write this as u times r to the minus first power and apply the product rule. I think it's much simpler, but if you like to use the quotient rule, it's up to you, it doesn't matter. So first this will be du dr times 1 over r, and then it's going to be minus, this goes down, so we get u divided by r squared. So this is going to be this, and where does this go? This is going to go in here, so this will be multiplied by r squared. So something that would be useful to do, obviously you can just not do it or do it later, because this will be multiplied by r squared, we can factor out r squared here. And in order to do that, we will have to multiply and divide here by r, so that we get r divided by r, so that in the denominator now we have r squared. So let's factor out 1 over r squared. So we get r times du dr minus u. Okay, and now let's plug in here. So what is d by dr of r squared dr? Well, when we multiply by r squared, it's going to cancel this part right here, so we only get what is in here, and now we have to take the derivative of it. So in this first term, we apply the product rule once again, and when we apply the derivative to r, it's just going to be 1, so we get du dr, and now we get plus r d squared u dr squared, and the derivative of u will be minus du dr. So these two du's will cancel out, so we only get r d squared u dr squared. So we can see that using this substitution, does indeed make this simpler. So now instead of having this thing, which was very much a mouthful, now we have r d squared u over dr squared, which is much simpler. So we have a better chance of solving this equation. Obviously, this is something that coming up with the right substitution is not easy. As I've said before, it does require experience, but it helps to know what the problem is, which is something I always repeat here. So if you see which part of the equation is causing you problems, you can try and see what sort of things you could do. So as we just saw, this part right here is just going to be r d squared u dr squared, and we can see that the substitution that we use, this u substitution, helped us make sure that there is not going to be a first derivative in our differential equation. Now there's only the second derivative, which will make it much easier to solve. Well, this part right here will remain the same. So we get minus 2m r squared divided by h bar squared. The difference, though, is going to be that this time we are writing this not in terms of r, but instead of u, which, remember, is just going to be r is going to be u divided by r, because u was small r times big R. So instead of this big R, we write u divided by r, and on this right side we get l plus 1 u divided by r. And now, well, here technically we are done with what we can do without specifying the potential. Obviously in this case we're going to use the potential for the hydrogen atom, but it is interesting to note that so far the procedure is the same regardless of the potential, and I'm going to try to keep it general for as long as I can, which is actually not much longer. So what I want to do now is, well, first of all, we got these r's here, which are kind of annoying, so let's just multiply by those. So when we do that, we get rid of those that are dividing, and we have now r squared. Now let's take this l plus 1 here and put it to the left hand side, and also take this energy part and put it to the right hand side. So when we do that, we get r squared d squared u dr squared, this hasn't changed, minus 2m r squared divided by h bar squared times the potential, and now minus l plus 1 times u. Oh, this is also times u, sorry. And now this is going to be equal to, well, here we have minus, but so it's positive, and then we have to put it to the right hand side, so it's going to be negative. So we get minus 2 m r squared h bar squared e times u. And now what we have to do is, I want to leave this in a way that is quite similar to the Schrödinger equation. So in order to do that, let's isolate the energy and also the second derivative. So to do that, what we have to do is divide by this minus 2m r squared h bar squared. So when we do that, this part right here, well, the r squared will cancel out, and we will be left with minus h bar squared divided by 2m d squared u dr squared. Here we have exactly the same, so this will just cancel out, and we get plus the potential times u, and here instead of minus l plus 1 u, we're going to have to multiply by the inverse of this. So we're going to get positive h bar squared divided by 2m r squared times l plus 1 u, and this is going to be equal to eu. And in fact, we can factor out here, just to make this a bit more evident, we can factor out the u in here, so we get this expression. And this actually is of the same form as the Schrödinger equation, but with the difference that we have this extra term. And usually what this here is called, this is called just the effective potential, and this part right here is what is called the centrifugal term. And well, this is as far as we can go without actually specifying the potential. So up to this point, the solution for all potentials that we might put into the radial equation, it's going to be the same. Okay, so what can we do now? Let's go to the next page and finally put into this equation the potential for the hydrogen atom. So what is the potential? Well, as we have seen in maybe in electromagnetic theory or electrodynamics or electromagnetism, whatever course you have had, the potential due to just some proton, remember, it's just going to be these charges of our particles, which will be 1 proton and 1 electron, so we can actually just leave it at E squared minus E squared, sorry, divided by 4 pi epsilon 0 times R. Okay, so this is going to be our potential, which we will now plug in here. I don't think I have enough room to write it manually, so I will just copy it. So it will be minus E squared 4 pi epsilon 0 R. Okay. Now we have to begin solving this equation. How can we do that? Well, let's take a look at it and see what our problems are, what makes this difficult. So first of all, there's a lot of constants everywhere. So we have this E squared, 4 pi epsilon 0 and h bar squared and a lot of r's and r squares everywhere. So the first step would be to just make the notation somewhat simpler. So let us first of all put everything that has just u to in the same place. So we could just take all of this and subtract it and put it to the right hand side. So let's begin by doing that. So minus h bar squared by 2m d squared u dr squared. Yeah, well, and all of this is going away. So now let's just say equal to, well, here we have the energy, so energy. Then we have plus this term plus e squared by 4 pi epsilon 0 r. And then we have minus h bar squared divided by 2m r squared l plus 1, and all of this multiplied by u. Okay, looking a little bit better. Now we can see that this minus h bar squared divided by 2m is showing up in several places, and you might recall that it might look familiar to you because we have used substitutions like that before. In fact, what we have usually been using has been this k squared, which was 2me divided by h bar squared. That's what we have been using constantly. Now, in this case, what are going to be the values of the energy? Well, we are looking for bound states to the hydrogen atom, right? Because if we wanted the atom to exist, it must be a bound state. Otherwise, it would just be scattering state where the proton and the electron will just repulse and go away, or whatever. It would just be scattering. It wouldn't be, they wouldn't keep close to each other. So it has to be bound state, which means the energy is negative, which means we have to include a minus sign in here. Now, we can actually use the substitution because this and this is quite close, but it doesn't have the energy part. So let's divide by the energy. So we divide all of this by the energy. So here we just get 1. Here we have E. Here we have E. And here we are also going to get E. Now we have several places where we can actually go ahead and use the substitution, but what happens here where we have this energy by itself? Well, we are going to get everything in terms of K, and the energy will be gone, so it wouldn't make much sense to just keep here this random E and everywhere else just as K. So we have to make sure that everything is uniform. So from here we can see what is the energy in terms of K. Well, the energy is going to be minus K squared h bar squared divided by 2m. We can see that directly from here. So now let's use the substitution in this equation. So minus h bar squared divided by 2me is actually 1 over this quantity right here. So it's just 1 divided by k squared d squared u dr squared. And this is going to be equal to, well, the 1 will still just be 1. Here we get this e squared. But what else do we have? Now, instead of this energy here, we're going to get minus k squared h bar squared divided by 2m. So the 2m will actually go in the numerator, and the negative sign will be up front. Now, what else do we have? We have now 4 pi epsilon 0, then we have h bar squared and k squared r. Now, in this part right here, once again, we have 1 over k squared, so we get plus 1 over k squared times r squared, and well, in the numerator there's also l plus 1, so let's leave that there, l plus 1, and this times u. Now this is looking somewhat better, but it's still messy. So what can we do about it? Well, we can see that here we have k squared dr squared. Here we have something we can write as k times kr, and here we have kr squared. So we can actually make this look a lot better if we change notations. Let me go to the next page. I'm going to have to erase a few things here. This should not have come with us, neither should this. So we can tidy up notation quite a bit if we just introduce, and also this was just a comment, no need to bring it. Okay, so we can tidy up notation if we introduce a new variable. We say, okay, some new variable rho will be k times r, because that way here we're going to just get a rho times k, and here rho squared. But what about this? So what is going to be d rho dr? Well, this will just be k. And what is going to be this derivative with respect to r? Well, we have to apply the chain rule as we have done before. So d by dr, this is just going to be d by d rho times d rho dr. And what is d rho dr? Well, it's just k. So this is just going to be k times d by d rho. And if we take the second derivative, it's just going to be k squared. So when we apply this here, let me change color, we're going to get k squared d squared u d rho squared divided by k squared. So this will actually cancel out, which is amazing because that's going to make notation much cleaner. Now this will be equal to, well, the 1 will still be there. We have a 2 and a 4 here, so that will simplify a little bit. And then we have minus m e squared. I like to write it in this order, even though it doesn't matter, divided by 2 pi epsilon 0 h bar squared k, and the other k times r will just be rho. And here it is still messy though. We see it's a little bit better, but we still have all these constants lying around. So we can actually just define some constant, which is usually called rho 0, but you can obviously call it whatever you want. And we can call it m e squared divided by 2 pi epsilon 0 h bar squared k. Basically everything here that is making this look messy. So when we do that, we can just rewrite this as minus rho 0 divided by rho. And just take a look at this. It is looking so much better. So this has been the objective so far, just make notation cleaner. We have finally this part right here, which will be plus l plus 1, and then we have k squared r squared. That is simply rho squared, and all of this times u. So this is now the equation that we have to solve. It is looking much, much better than before. However, that sadly does not mean that it's going to be easy to solve. In fact, solving this exactly is honestly really, really difficult. So what we're going to do is we're going to use the same approach that we used for the harmonic oscillator. What did we do back then? Back then we said, okay, so knowing what we expect this wave function to be like, because remember this u will be the radial part of the wave function. So knowing what its behavior should be, we can then basically guide and see what the mathematical form of this solution should be. And thus we can basically construct it by parts and multiply it together. So let's first see what happens to this equation when rho becomes very, very large. That means when our electron is very, very far away from the proton. So when that happens, this equation will become asymptotical to, well, what happens in here? This will become negligible. It's just something divided by the square of a huge number. And here it's just something divided by the square of a very big number. So both of these are going to be negligible compared to just the function u. So now this is what we want to solve. And this is actually quite easy to solve. We have done it many times before. Just write everything to the left-hand side, minus u, and we can factor this as d by d rho plus 1, d by d rho minus 1, and times u equals 0. And we know what the solution of this equation is. So what it's going to be is, this is going to be u, which is a e to the rho plus b e to the minus rho. However, we are in the case where rho is very, very large, which means that this term right here will be continuously growing and growing, so it will not be normalizable. It will not go to 0 as rho goes to infinity, which is something we need for these bound states. So this is not a physically acceptable solution. This does go to 0, so that is why it is fine. And we don't really need to write this constant of integration here, because we're going to be multiplying the results of several differential equations. All of them will have a constant of integration, and we might as well just include all those constants into just one and deal with that at the end. So this will be our solution for this particular case. Okay, so this is the first part that we want. Now let's go to a different scenario. We know what happens when rho goes very far away. And now please do not make this mistake. Do not go, okay, what happens if rho goes to minus infinity? You might think about that because we have to be doing that a lot when we're dealing with x. However, rho here is just the distance between the proton and the electron. And it doesn't make sense to be like, okay, what happens at minus infinity, because the distance can go to 0, from 0 to infinity. You can't really have negative values here. So don't make that mistake. The second case that we want to take a look at is what happens when the distance becomes very, very short, so when it's close to 0. Well, then this will become asymptotical to what? So we get d squared u d rho squared. Well, in that case, if we go very close to 0, this term here will dominate. It will be divided by a very small number squared, so this will be very large. So this is what is going to dominate here. So this will be asymptotical to L plus 1 rho squared u. Now, the solution to this differential equation may be somewhat tricky, because here you have to see, well, we are here dividing by rho squared, and we're also taking the second derivative. So our solution here should be some sort of polynomial. So if we have rho to some power, let's just call it s. If we have rho to some power, if we take the second derivative of it, right, if we get d squared of this thing right here, just d of this function, d rho squared, and this is going to be u, right? We're looking for some u of this form, so we take its second derivative. We're just going to get s times s minus 1 rho s minus 2. So, and why do we know that it has to be like this? Because the right hand side is going to be divided by 2. So L plus 1 rho squared u. If we plug this sort of solution, we're going to get L plus 1 divided by rho squared times rho to the s. But here this is just dividing by this exponential, so it's basically just minus 2. So we can see that this will have basically the same shape as this. And this is just the left-hand side of the equation. This is just the right-hand side of the equation. That's why we know that we have to go for a polynomial here. But once again, as I have said, solving differential equation is also kind of an art. There's not always going to be just one way to go about it. And sometimes it does require you to have some experience with differential equations. But this is how I would approach this equation. So now let's put left and right hand side together. So we see that if the solutions are of this shape, then we get L plus 1 times this. This is equal to s minus 1 times rho s minus 2. So for this to be equal, we need L plus 1 to be equal to s minus 1. So let's now go ahead and multiply through to see what allowed values of s we have. So we are going to get L squared plus L. This is equal to s squared minus s. How can we solve this? Well, what I would do is just put, well, it doesn't really matter which side, but let's go for L squared plus s squared. This is equal to minus s minus L. And in fact, let us put everything to the same side. So actually, let's add these together. So we're going to have plus s plus L equal to 0. So now this right here, oh sorry, this is L minus S squared, my bad. Yeah, so L minus S, and we have L plus S. Okay, yes, that is correct. So now let's factor this as L plus S, L minus S, and then we have plus, and actually just to make it more suggestive, I'm going to write it as L plus S equals 0. So now we have L plus S here and L plus S here, so we can actually factor out L plus S, and it's going to be multiplying L minus S, and it's also going to be multiplying here 1. Okay, so what are going to be the solutions of this? Well, one solution is when this is 0, one solution is when this is 0. So this means S has to be minus L, or S has to be, will have to be, let's see, L plus 1, so that when we take minus S, it will be minus L minus 1, and this will be 0. So that means that our solution will be of the form, in this case, U will be rho to the minus L times some constant, which I'm not writing here because of what I said before. I'm just going to put one constant in front at the end. Rho to the minus L plus rho to the L plus 1. These are the two mathematically allowed solutions. However, which one of these is physically allowed? Well, we are in the case when rho is very, very small. So let me write this like this. Instead of rho to the minus L, this is 1 over rho to the L. So when this goes to, when rho goes to 0, this term will blow up, and that's not something we want. So we have to discard this first term, and we will only be left with rho L plus 1. So now we have two of the solutions that we want. We have considered two of these behaviors. So let us then put all of our solutions together so far. So we know that when rho grows very, very large, we want this to behave as e to the minus rho, because now we see that it's going to be going to 0. Then we want to have the behavior when rho is going to 0, which, as we just saw, will be rho to the L plus 1. And finally, we want some other function, some v of rho, which will be this function basically in between. So now we want to take the derivative of this equation and plug them into our differential equation. And then we are going to want to solve that equation, which should be, in principle, solvable and easier to work with. Now let me go back to the differential equation. Here it is. And where were we here? Okay. So in order to be able to use this, we have to now take its second derivative and just plug it in here. That's what we want to do. So, well, let's start deriving. This will be quite annoying, but, well, there's nothing to do about it. So, first derivative, I'm just going to write it as u prime. What will this be? This will be minus e to the minus rho times rho L plus 1 times v. And this is product rule, so now we have to multiply the second term. So we get plus e to the minus rho times the derivative of rho L plus 1, which will just be L plus 1 rho to the Lth power times v. And finally, the derivative of this. So we will have plus e to the minus rho to the L plus 1 v prime. So this is the first derivative. So far, it's not too bad. Now let's take the second derivative. So when we do that, this term right here, we get another minus sign. So we just get e to the minus rho, and everything else stays the same. Now we derive the second part. So now we have minus e to the minus rho, L plus 1 rho to the Lth power times v. And finally we derive this, so it's going to be minus e to the minus rho to the L plus 1 v prime. Okay, now let's go for the second part. So we get once again minus e to the minus rho, L plus 1 rho to the Lth times v. Time to derive this now. I'm going to put the L plus 1 in front. L plus 1 times L e to the minus rho to the L minus 1 times v. And the final part will be, let's see, L plus 1 e to the minus rho to the Lth v prime. Finally, we need to take the derivative of this, which is going to be minus e to the minus rho to the L plus 1 times v prime. Here, just make sure to take your time. You don't want to make an algebraic error here or just a dumb mistake deriving, because it's kind of an annoying procedure, so make sure to get it right the first time, and so you save yourself some trouble. So it's going to be plus e to the minus rho L plus 1 rho to the Lth power v prime, and finally plus e minus rho to the L plus 1 v prime prime. Okay, now we need to simplify this. I'm going to take this to the next page so that we can put everything that has a v and a v prime together. So let's see, this I'm going to change color so that we know that this is a different case. U prime prime, well, let's put everything with just v together. So, and by the way, we can actually see that everything here is multiplied by e to the minus rho and rho to the Lth power. So actually, let's just simplify that a little bit. So e to the minus rho to the Lth power. Okay, and now factor out the v. So everything that has a v. So this part right here, we took out the e to the minus rho, we took out rho to the L, so all we are left with is rho. This right here, we took out this, so now we're just going to have plus L plus 1. This is, and we already considered this and this. This is v prime, here's another v, so now we will have minus L plus 1. Oh, this is minus, by the way. Whoops, good thing I noticed that. We do not want to be making dumb mistakes right now. Okay. Then we have this part right here, which is going to be plus L plus 1 times rho to the minus 1 power. So basically just divided by rho. So we already considered this, and that's everything that has only a v. Now let's go with the v primes. So here we're going to have minus rho from this first one. Here we're going to have plus L plus 1, and there's still these two. So then we have minus rho from this one, and here we have plus L plus 1. Okay, and finally we have to include, let me see, did I put all the parentheses? Yes. And finally we have this, which is just rho v prime prime. Okay, now there's a few more simplifications we can do, because here, well, this is just minus 2 times L plus 1. So this is basically just minus 2 L plus 1 plus this right there. And here we have minus 2 rho and plus 2 L plus 1 plus 2 L plus 1, and we can just get rid of this. Plus, whoops, that does not look like a plus, plus rho v prime prime. Okay. I'm going to take this to the next slide if I can. Okay, there's a few things I didn't want to bring, but oh, I don't want my camera to cover this. Let me move it a little bit. Okay, that's fine. Now, what was our differential equation? It was just this right here. Control C, Control V. I need to erase this now. So this was our differential equation. So now let us plug this second derivative into this right there. And also remember u, just to make sure, u here is now going to be e to the minus rho to the L plus 1 times v. So we are going to put that in here and this in there. Okay, let's do that. So well, when we take the second derivative, we're just going to get exactly that right there. Actually, I'm just gonna go ahead and copy it. I really don't feel like writing it down again. Okay, so we get this, and that is going to be equal. Let me stick to blue. I wanted to change color, but since I already copied it, this will be equal to e to the minus rho to the L plus 1 times v And all of this is multiplying 1 minus rho 0 divided by rho plus L plus 1 rho squared. So here, as we can see, we have e to the minus rho on both sides, but here it is r to the L, and here it is r to the L plus 1. So let us just multiply through by 1r, so that we get r to the Lth. And when we do that, this one here, oh, by the way, I'm missing a parenthesis, that one will be a rho, this rho will go away, and this rho squared will just be rho. Okay, let's go to the next slide and continue working with this. Okay, so now let's put everything to the same side. So let's just say everything to the left. Doesn't really matter, but let's do it that way. So we have e to the minus rho to the Lth. And this is going to be a factor of, well, let's put everything together. So first, I'm going to begin by putting the second derivative. I like to have it first, so rho v prime prime. So we already considered that. Let's now go for the first derivative. Now here, this does not include anything about the first derivative, so we can just leave it the way it is. So plus v prime minus 2 rho plus 2l plus 1. And then we're going to have everything including just v. So let's see. Well, when we subtract this rho is going to cancel this rho. Okay, so there is that. And also, let's say when we subtract this part, it's going to cancel out this part right there. So actually, what we're going to be left with is just going to be this positive rho, because we have to subtract by it, so it's going to be minus minus, which is now positive. So we get rho 0 minus 2 L plus 1. And this has to be equal to 0. Now, we have got now what is a manageable equation for a manageable differential equation, because now there's nothing being divided by rho, which was kind of annoying. It's just a straight up differential equation, which we can solve by using a power series method. Now, we have done that a few times before. I'm obviously going to go through it again. You know, in this channel, we always go through it, so let's do that. Now, what again does it mean to go for a power series solution? We're going to say, well, we are going to go for solutions that are linear combinations of polynomials. So that means that our solution v, which will depend on rho, which will just be the sum from j equals 0 to infinity of some coefficient times some power of, sorry, not of x, of rho. Okay, so what does it mean? Well, what is then v prime? Because we need to write v prime, and v double prime in terms of this summations. So v prime is just going to be the derivative of this. This is just a sum, right? This is just sums of polynomials. So the derivative is just going to be the derivative of each one of these terms. So it's just going to be j equals 0 to infinity of a j times j rho j minus 1. And the second derivative, very similarly, will be just the derivative of this, which will be sum of j equals 0 to infinity of a j times j minus 1 rho to the j minus 2 power. Now that we have this, we can plug it in here, and notice that the equation that we are actually interested in is only what is inside of these parentheses. It's not really this part right here. We want this here to be 0, not that part. So this is what we want. So let's now plug this into that equation. Okay, I'm going to go with blue. Okay, so rho times v prime prime. That's going to be rho times this. So we're going to get the sum of j equals 0 to infinity a j, I don't know why I put that parenthesis there, j times j minus 1, and we had rho to the j minus 2, but this is multiplied by rho, so this rho will multiply each of the terms in the summation. So instead of being rho to the j minus 2, it will be j minus 1. Now we have this first derivative here, and notice that we have to multiply it by minus 2 rho plus 2l plus 1. So we are going to have plus, let's write it like this, 2L plus 1 minus 2 rho. And this is multiplying the summation from j equals 0 to infinity of aj j rho to the j minus 1. Now, this is just a constant. This has a rho. So let us actually multiply through, and we are going to get two summations. So one is going to be plus 2L plus 1, which we can just leave outside because it's just some constant. And the argument of this sum will be the same. It will be unchanged, aj rho to the j minus 1. But now we have this minus 2 rho. So when we now write the second summation here, we're going to get minus 2, which is a constant. We leave it outside. But now this rho will go up inside and multiply each of our elements. So it will be j equals 0 to infinity of aj to the j times j times rho to the jth power, because it was j minus 1 times rho. Now it is just rho to the jth power. So instead of writing this, we are going to, we're going to use now what I just wrote down. Okay. Now we have this final term, which all of this is a constant. Rho 0 minus 2L plus 1, all of that is just a constant. So we can just leave it outside of our summation. Minus 2L plus 1 times the sum j equals 0 to infinity of aj rho to the jth power, and this has to be equal to 0. Okay, so this is now our equation. It might look worse, but it is going to be much simpler. Now, remember, how do we solve this sort of equation? What we do here is we want to put all of these rows to the same power. So basically, here is rho to the j, but here it is rho to the j minus 1 and rho to the j minus 1. We want everything to be in terms of the same power so that we can put all of this into just one sum. That is what we want to do. So let's see, this right here is a problem. What can we do about it? Well, notice that j equals 0 is actually 0. If you put j in here, you get 0. So this sum actually doesn't really begin at 0. We can just say, okay, it begins at 1, even though actually 1 is also going to be 0. But we can actually write this like this, and there's going to be no noticeable difference. And now we can make a change in these this index. Instead of naming it j, we can basically call it j plus 1. And in order to compensate, this would have to start 1 instead of at 1 at 0. Right? This is just a standard thing that you can do with summations. We're just going to say, okay, instead of being j, it's going to be j plus 1. So before this first term was 1, now the first term has to be 0 to compensate for the fact that we are pushing everything forward. So j plus 1, this j minus 1 will now be j plus 1 minus 1. So this will be just j, and this j will be j plus 1. So actually we can write this as j times j plus 1. And this will be rho to the j plus 1, j minus 1 plus 1, which is just j. And this will be a sub j. This will now be a j plus 1. If you're not sure what I did there, well, in Spanish it's called regla del reloj. It's basically the clock rule. I'm not sure what its name in English is, but it is a normal rule for summations. And if you're not too sure, it is good to look it up because it is used very, very often in this method. Now we are going to do the same thing here. This, when j is 0, this is actually 0. So we can just say, okay, it begins at 1. And now we are going to apply this rule and change all of our j's to j plus 1. That way we are going to get a j plus 1, j plus 1, rho to the j, and j now has to begin at 0 to compensate. Because before, the first term was j equal 1, and it was basically the same thing that it is going to be if you just put j equals 0 in here, right? You can compare those two expressions, they are the same. And now everything here has rho to the j. So let's factor that out. Put everything into the same summation because everything starts at with the same index and it has the same rho j. So let's factor out this row to the jth, and we have a j plus 1 times j times j plus 1. Then we have here plus 2l plus 1 times j plus 1 times a j plus 1, and then we have minus 2aj times j, and here we have plus row 0 minus 2l plus 1 aj, and this has to be equal to 0. Okay, so in order for this to be 0, each one of these terms has to be 0, always. Because our solution would be for row to be 0, but then we wouldn't really have a problem here. So that's not really acceptable. This has to be 0. This means that I'm also going to factor here aj plus 1, factor of j plus 1, plus 2l plus 1, j plus 1. Then we have, I'm going to factor out this aj, so we get plus aj, and then we have, let's see, minus 2j plus row 0 minus 2l plus 1. There we go. This has to be equal to 0. So now let us work with this, and with this we can actually determine the recursion relationship. Because remember, that is, I don't think I clicked Control C here. Our goal in these problems is always to determine this recursion relationship, or relation that will let us find the polynomial that we're looking for. Okay, now what is this going to be? Well, let us just isolate a j plus 1 so that we can get this recursion relation. So let's put this to the left hand side. When we do that, we're going to get 2j minus row 0 plus 2l plus 1, yes. And this will be multiplied by aj. And in the denominator here, take a look at, we can actually factor out here j plus 1, because this and this is multiplied by j plus 1. So we get j plus 1 factor of j plus 2l plus 2. Okay, and this is actually going to be our recursion relation. We can write it a little bit cleaner here. Just say aj plus 1 is going to be 2 times j plus, oh, this is not j plus 1, this is j plus 2. Sorry, small mistake there. This is, whoop, plus 2. So we get j plus l plus 1 divided by j plus 1, oh, and minus row 0, aj, j plus 1, j plus 2l plus 2. Okay, great. Now this is our recursion relation. It might not look very good, but this actually lets us construct our solutions, and it does depend on L, which is similar to what we saw in the previous case with the in the angular equation, where our Legendre polynomials and thus also the associated Legendre polynomials depended on the given L that we have. So in order to actually determine this, we need to know L. And here we have to notice something else. So these terms will just continue to increase and increase. And in order for this to be a normalizable solution, and our solution not to just continue to grow, we're going to need there to be some maximum value for these coefficients. You can't just go forever with your summation. You need to have some maximum value. That means that we're going to need that at some j, because j is the coefficient that tells you, that indicates the sum, right? The summation is in terms of j. So this means that here, in order for this to be 0, the numerator at some j has to become 0. Otherwise, it will just continue to grow. So 2j plus l plus 1 minus row 0 at some point has to be 0. And that point will be when this j is some maximum j. And this is actually going to be, this is what we're going to demand from our solution, so that this is indeed the solution that we want, and that is physically acceptable, not only mathematically, but physically acceptable. And here we can see that rho 0 is just a constant. L is something that depends, that we basically have to give to our problem. We have to tell them what this L is, or find it out somehow. And this J depends on whatever term we're dealing with. So actually this right here is what kind of controls our solution. Given L, then there's going to be some condition for J, and this is all that can change. So that's why this part right here is something that we are going to call N, which you might recognize as the principal number of this atom. So we're just going to call this 2N, and this is going to be equal to rho 0, right? If you just put this to the right hand side. And already this is going to be very, very interesting, because N is going to give us a lot of information about the atom. We don't really know much right now about N, so let's try to find out a little bit. So what is rho 0, right? I'm just gonna write it down. Let me see if I can find it somewhere. 1 second, where's our rho 0? Oh, we've spent a lot of slides. Let's see. Rho 0, oh, I think I must have skipped it. 1 sec. Let's see, u prime prime. Let me see where our rho 0 is. There it is, there it is. Rho 0 is this quantity right here. So let me now go back to where we were. And I'm almost there. There we go. So rho 0 was just this quantity. So let's plug it in. So we're going to get that 2N is going to be equal to m e squared divided by 2 pi epsilon 0 h bar squared k. But what is k? Remember, k is minus 2m e divided by h bar squared. So now we actually are going to get some relation for our energy. So let's write here, instead of k, the energy. So since we're dividing by k, this is going to be minus h bar squared divided by 2m e. And well, the square root of all of this, right? So now in order to actually determine this, we're going to have to square all of this. Now it's going to be 4n squared. This is equal to m squared e to the 4th power to, well, 4 pi squared epsilon 0 squared h bar to the 4th power times minus h bar squared 2m e. So now let us solve for e. So multiply by e, divide by this. So we get that the energy that's actually going to depend on this number n, so we can write it as e sub n. This will be, well, let's take a look at this. So m squared, this square will cancel out this m. H bar squared here will cancel out this 4, so we get h bar squared. And okay, yeah, that's about it, I think. So what we have still in the numerator, we have, well, minus m e to the 4th power, and then we have 4 squared pi squared epsilon 0 squared h bar squared times 2, right? Let me see. You have the minus sign, the m, the e to the 4th, 4 squared because of this one right here. Oh, I'm missing the n squared. Quite important. Okay. Everything else is in there, right? The 2, yes. Okay, and we can actually write this a little bit differently, just so that it resembles what you usually see in textbooks. So we get minus m divided by 2 h bar squared e squared divided by 4 pi epsilon 0 squared, and all of this will be multiplying 1 over n squared. So we can actually see right here, well, the energy depends on n, and we can actually go ahead and calculate the energy because all of these constants are known. This m, by the way, please don't confuse this m with the number that we found before in the angular part. Well, it was some integer. This is just the mass of this electron. Okay, so we have this amount, and we can see, well, the lowest energy then will be when n is equal to 1. The greatest, because this has the minus 1. So the ground state will actually be when n is equal to 1, and ever after that we're just going to be continuing to grow from that. So we can see that when n is equal to 1, our energy will be of the ground state, which we can even use these numbers to find, and we can see that it's going to be the minus 13.6 electron volts, which is actually an extremely important result, because using this method, we now basically verified what Bohr had predicted with the use of some premature quantum mechanics, but we now solved it using actual quantum mechanics, and that is a pretty big deal. So we know that n equals 1 here would be this value, and what values for n could we even have? Well, that comes from this relation right there. We know that n is just J max plus L plus 1. So we can see that J max is going to be n minus L minus 1. So given some L, we can see what values for n we can have. So let's say we have L equal 1, for example. Then what we have here, J max here, for some n, well, we will have n minus 2. So J max has to be at least 0, right? Because it has to have at least the first term of the series. The series begins at J equals 0. So if L is equal to 1, then n, well, it's going to have to be 2. And if L would have been 0, then n would have been 1. But there is really no situation where n could be 0, because if n is 0 and L is 0, it's still going to be minus 1, which can't be. So n has to be at least 1. And it can also then be 2, 3, 4, and so on and so forth. Right? But it always has to be greater than L. So L can also be 1, 2, 3, and 4. It also has to can be integers, as we saw before, but its maximum value is always going to be just n minus 1. Because if they were the same, in this expression right here, we would have, if they are the same, these two cancel out, and we still have this minus 1, which would tell us that our sum starts from the minus first term, which would not make sense. So that's actually where these conditions come from. And remember, the quantum number m, do not confuse it with the mass that we were discussing earlier. The quantum number m can have values from minus L to L. So that means that there are 2L plus 1 possible values for m, because if it's, let's say that L is 2, you can have minus 2, minus 1, 0, minus 1, and plus 1 and 2. So if your L is 2, you have 2 times 2 plus 1, 5 possible values of m. So now we can finally see all the relation between our quantum numbers, which are n, L, and m. And these are the numbers that we need in order to determine the solutions. Because remember, in these polynomials that we just found for the radial equation, you need to know n and L. But for the associated Legendre polynomials, you needed to know L and m. So if you know n, L, and m, you can construct the wave functions for basically any, for whatever state you are interested in. And we saw that n equals 1 will be the ground state, and then n equals 2, 3, and 4 will be the excited states after that. So what then are our solutions? So we found that this recursion formula gives us this sum, right? This gives us the solution to this v function that we have determined, this v of rho. Now this recursion formula is actually well known, and just as in the case of the angular equation, our solutions were the Legendre polynomials and thus the associated Legendre polynomials. In this case, the solution are the associated Laguerre polynomials, which you write with an L. And obviously this will depend on n and L. Now they also have a generating functions and orthogonality relations, and there's many properties. It's a very well studied group of polynomials. So if you're interested, maybe we can do a video about it, but to be honest, that's more of a mathematical part than physical part. We are only interested in generating it. You can determine it using the recursion relationship or just by the generating functions that mathematicians have developed for these particular polynomials. But in the end, it's going to be up to you. And in our examples that we'll do in the next video, we're just going to use a recursion formula for now because it's a bit more tricky. And it also lets you play more with this n at L values. So our solutions to the radial equation, R, n, and L, what are they going to be? Well, remember, we know that our u, that depends on rho, this will be what? It will be e to the minus rho, rho to the L plus 1, and now times these Laguerre polynomials. But this is u, and this is in terms of r. We want this to be r, big R, in terms of small r. So here, u, remember, u was small r times r. So this is actually small r times r. So big R will be what? It will be 1 over r times this. But instead of rho, remember rho, what was it? Rho was 1 over, actually I think it was kr, right? But we can actually rewrite k now as well. So k, it was the square root of minus 2m e divided by h bar squared. But now we have even determined what the energy levels are. It was, where was it again? Here it is. We determined what the energies are. Let's see there. So we can now write k in terms of this. So, and the whole idea of this is to leave it in terms of constants and our quantum number, not in terms of this arbitrary constant that we invented, right? These are natural amounts. This is something we invented. So let's see. So it's going to be square root. The minus will cancel out here. And we can see here, by the way, energy is negative as we expected because this is a bound state. So we get 2m divided by h bar squared times m divided by 2h bar squared e squared 4 pi epsilon 0, all of this squared, times 1 over n squared. So now we take the square root of this. Well, the 2's will cancel out. Everything else is going to be squared. So we're going to get m divided by h bar squared times e squared 4 pi epsilon 0 times 1 over n. And here we can just go ahead and define this right here to be a, which is actually called the Bohr radius, m e squared divided by 4 pi epsilon 0 h bar squared. And with that we can now write rho as just, let's see, actually if this is, yeah, we actually have to define a to the minus 1 like this. So it's the other way around in order for this, the units to make sense. And that way rho will be 1 over a n, right? Because this is 1 over a, this is just 1 over n, and k, when you put it in there, it's going to be 1 over a n times r. So we can actually just write it as r divided by a n. So now let's go back to our solution for this r. So if we take a look at this, what it's going to be? Actually, I don't know, I'm writing it twice. Let's go back. So we're writing this r function, which was just u divided by r. So we had 1 over small r e to the minus rho. But what is rho? It's just r divided by a n. Then we have rho to the L plus 1 power. What is rho? It's r a n to the L plus 1. And finally, we have these Laguerre polynomials, which we will have to evaluate instead of rho as r a n. But we can just write as the Laguerre polynomials. Okay, so this is our solution. This right here is what we were looking for. This is the solution to the radial equation. And remember, the radial solution was actually not the solution to our problem. We were looking for psi, which we wrote as some radial function of r times some function of theta psi, which we found to theta phi, sorry, that we saw is actually are the spherical harmonics. So let's now put all of our results in here. So we're going to see that psi will depend on L n, L, and m. And this, what will it be? It will be, well, some constant of integration, right? Some constant times what we have right here, which is 1 over r e to the minus r a n times r a n l plus 1 times these Laguerre polynomials times these spherical harmonics. Now this depends on n and l, and these depend on l and m, theta and phi. So this is actually our solution. Now the constant of integration here, well, we already have found the one for the spherical harmonics, so this is actually from the radial equation, and it can be found by using the orthogonality relation of the Laguerre polynomials. However, I have looked into that and I think it's a little bit beyond what we are interested in, so you can just go ahead and use the one that is given in the textbooks, because usually this is just a general one for any NLM. Later we will see that if you want to find it, you can just use these formulas to find the psi for a given n, l, and m, and thus we can just go ahead and just normalize whatever solution we get, and it's going to be much simpler than going for a general case. So this is the solution to the hydrogen atom. In the next video, I'm going to just use this formula a little bit, determine some of these states, take a look at them, and after that we can just find a few expectation values, and with that we will be done with this part of the course. So if you have any questions, make sure to let me know, and I will see you in the next video.